For this problem, we're given an integral in polar, the integral from pi over 4 to pi over 2, that's the angle bounds. The integral from root 2 over sine theta to 2, those are the r bounds of r cubed. And we're asked to re-express it in rectangular. To even begin to approach this problem, we have to figure out what the heck this region is. And to figure out what the heck this region is, we're going to make a sketch. Okay, the theta bounds are nice numbers, so we're going to start with them. One of our theta bounds, our lower bound, is theta equals pi over 4. That's a line at 45 degrees, and it just goes on forever. And our upper bound is theta equals pi over 2, which is a line at 90 degrees. And so we know that whatever our region is, it's gonna live within this wedge, although it's pretty strange within this wedge because the r bounds depend on theta. So now we're gonna work with the r bounds, and the upper bound isn't bad at all. It's r equals 2, so that's not bad. That's a circle of radius 2. It's the lower bound that's challenging, and the lower bound is r equals root 2 over sine theta. Okay, so we're going to manipulate that so that we can figure out what this lower bound is. So r is equal to root 2 over sine theta, which means that r sine theta equals root 2. It's always easier to graph if we're living in rectangular coordinates. So we're going to turn this into a y equals root 2. And that's because we have a lot more experience graphing in rectangular than in polar. So this is y equals root 2. So now we have to figure out where the heck root 2 is along this line. And I'm going to put in the coordinates of this point. This point is over 0 up 2. And what about this point? This point is at 2 cosine pi over 4 to sine pi over 4, which is root 2 comma root 2. So a line at a height of root 2 is going to go through that point. And so it goes across like this. Okay, and so our region of integration was the lower r bound, so we're going to go out along a radius, out along a radius, out along a radius, radius. This is our region of integration. Since we want to convert coordinate systems, our next job is to figure out how to describe this region in rectangular coordinates. To describe this region in rectangular coordinates, we're going to want to remember what the equations are for these two lines. So what matters? This theta bound isn't really impacting our region at all. We will just need to know where that bottom corner is. I think vertical strips, it sounds like a great way to do this integration, although it doesn't matter. Horizontal strips would go from this axis out to this function. Vertical strips would go from this line up to this function. So vertical strips, this is the line y equals root 2. This is the line r equals 2. So x squared plus y squared, the square root of that equals 2. So x squared plus y squared equals 4, which implies y equals the square root of 4 minus x squared. And we want the positive square root, not the negative, because this is in the upper half of the plane. This would, if the function were down here, we would want the negative. So this is the function for that upper line. This is the function for that lower line. So our integral is going to be the integral from the lower line, root 2 up to the upper line, root 4 minus x squared. And what are our x bounds? Well, we're going to look for the shadow of this region in the x on the x line, and it goes from 0 out to this point, which we found on the previous slide ended at x equals root 2. So our x bounds are from 0 to the square root of 2, and that will be dy dx. And our next task is to figure out what this function is. Okay, for the function, we have this r cubed dr d theta. And this is tricky. We need to remember that one of these r's is actually part of the r dr d theta, our area element. So our function is r squared multiplied by an area element, r dr d theta. So this integral is the integral over a region of r squared dA. And it's the r squared function that needs to be converted into rectangular coordinates. R squared is luckily pretty straightforward. In rectangular, it becomes x squared plus y squared. So we thought about the region first. What we did with the region was we created a graph of it, and then from that graph, along with from the equations that we found by setting r equal to each of the bounds, we were able to write the region in rectangular as though we had just been given a graph of a region that we were told to write in rectangular. And then we had to think about what dA was for this system, because we knew that dA was turning into dy dx. And then finally, we had to think about what the function was, and we had to convert the function from polar coordinates to rectangular. So those were all of the steps that were involved in converting this integral to rectangular.